everybody's doing really good. Last time, we introduced the displacement, D. That's not good. Which we said was a vector, meaning it had a magnitude and a direction associated with it. And of course, this magnitude was how far. And we did some simple vector addition. Primarily, we took one displacement, where a person would say walks from here to here. And then we call this D1. And then we went a little further, D2, and we said that the net displacement, that is the total displacement for the entire travels, for the entire path, was a vector that pointed from the start to the finish. And clearly, this D, we could write this as a vector addition. And it simply was, in this case here, the length of this one plus the length of that one. We then had another case where we had first a displacement, D1. And then the next displacement was the person walking in the opposite direction. This would be D2. Oops. And this case here, the net displacement D, again, points from the start of the path to the end. Okay, so that's kind of where we left off. And last time I ended it by saying that we were going to have to start talking about vector algebra. And that's what we're going to talk about today. Okay, now, if you were going to talk about any kind of algebra, you have to know the rules. An algebra, there's a lot of algebras out there. There's real algebra, there's complex algebra, there's Clifford algebra, there's a whole bunch of it, quaternions. These are all algebras, and you have to know the rules. Vector algebra is no different. What is an algebra? It essentially contains things and how to combine them. All right. So what are the entities in vector algebra? Well, there are vectors and scalars. So a scalar quantity is just an amount. It's a property that doesn't have any direction associated with it. So for example, the mass of a body, it could be 4 kilograms, right? And how big is 4 kilograms? Well, that's like 4 textbooks. That's a lot of mass. But notice you don't say 4 kilograms in the downward direction or the upward direction. You just say 4 kilograms, right? Volume is another scalar quantity. Time, how many seconds? That is a scalar quantity. There's a direction associated with time, like time always moves forward, but we're not talking about that kind of direction. Okay, we're talking about a geometric direction here, and time is a scalar quantity. Okay, vectors have an amount and what? Direction. Gotta have both. And so an algebra basically asks, how do you combine these things? Okay, so I'm going to just kind of lay out the general rules. Let me see if I can give me a better marker. So we're going to represent a scalar with S and a vector with B. And so what we'd like to know is, what about a vector added to a vector? What about a vector added to a scalar? What about a scalar added to a scalar? What about a vector multiplied by a vector? What about a scalar multiplied by a scalar? And what about a scalar multiplied by a vector? And these are about all of the combinations you can think of. You could put minuses in here, right? You'd say, well, not only is it about adding vectors, but subtraction as well. And so when we talk about addition and subtraction, we call that summation, okay? So we want to sum vectors, we want to sum scalars. We want to know what happens when you sum a vector with a scalar and also the multiplication. And also, I should mention, we have vector divided by a vector, vector divided by a scalar, and a scalar divided by a scalar. And that's just about everything you could possibly think of. Okay, so now I'm going to eliminate the ones that we don't do, okay? First of all, you cannot add a vector and a scalar together. They're completely different types of entities. So you really just can't do that. So you will not be asked to ever add a vector to a scalar. It wouldn't make any sense. This has a direction associated with it. This one doesn't. So how would you combine them? It doesn't make any sense. Also, you cannot take a vector and divide it by a vector. How do you add two scalar quantities? Well, these are number. This is a number. This is a number. How do you add them? Just like you add any kind of numbers. What's 4 plus 3? It's 7. Right? If you have 4 kilograms and you add 3 kilograms, those are scalar quantities. Remember, mass is a scalar. What do? You get 7 kilograms. And so these things add and subtract like regular numbers because that's all they are. Okay, so this is easy. It's trivial. We've done it all our lives just about. Okay. What about multiplying scalars and dividing? These are just numbers. So they multiply and divide just like everything else. If you have 4 times 3, you get 12. And if you have 4 divided by 2, you get 2. So this is trivial. And so is this. So that really leaves this, and this to kind of worry about. So, and that's what we're going to look at. Okay. Now you might ask, oh, I forgot to mention, V times V here, you can multiply vectors. However, we don't do that in this class. This is for physics 4A. We don't do it. So that's all we're left with is, these are trivial. We already know how to do those, and we have to figure out what we mean by this. Okay, so what I'm going to do first of all is attack this one right here. What happens when we take a vector and we multiply it by a scalar? And I'm going to give you an example. First of all, I'm going to represent the vector, as we did last time, with an arrow. The arrow represents the vector. The length of the vector, the length of this arrow, physical distance here, is a representation of the amount, the magnitude. The magnitude. Okay? So in other words, if this is 2, then this would be a length of 4. Because this has a length twice that one. So everything is scaled accordingly. And it's a really good idea to try to scale your vectors to represent the actual lengths of things, the amount of magnitudes. It will tell you if you got your answers right or not. Okay. So I'm going to go ahead and erase this. And we will give this vector here a label we'll call vector A. A with a little arrow on top means what? Vector A. Now, I also should mention the direction the arrow points is the direction of the vector. Simple. Now, what happens if we take A and we multiply it by a number? Scalar, which is a number, times, well, a number or a variable, but it's not a vector, it's just a quantity, an amount. We take S and we multiply by V, what happens? Well, this thing does nothing more than stretch or compress the arrow. So first we'll do only positive numbers. So if this is A, I'm going to leave the 2 off here. If this is A, then what does 2 times A look like? Well, this is our vector multiplied by a scalar, and it says take A and make it twice as long. And so 2A would look like now maybe more like this. This is 2A. The 2 basically just says take A and double it, double its length. Now notice something else. The vector is defined only by its amount and direction, not its placement. So this vector is A, but then so is this one. If this vector has the same length and the same direction as this one, they're the same vector. That tells us that we can move our vectors around everywhere we want as long as we maintain their length and their direction, right? So we can take this arrow, say here's another vector. And I can just move it around however I want. I have not changed the vector at all. Okay. So what if we multiplied our vector by 0.5, a number smaller than 1? In this case, this number being smaller than 1 causes A to shrink. In this case, it shrinks by 0.5, 1/2. So if this is A, this would be 0.5 A. Same direction, but half the length. And that's important to remember, is that when you multiply a vector by a scalar, you don't change its direction. You only change its length, with one exception. If I multiply by negative 0.5, however, the 0.5 shrinks the arrow by a half, shrinks the vector by 1/2, the negative flips it in the other direction. So if this is A, then 0.5A might look something like this. Negative 0.5A would look like that. Shrink it by a half, flip. The negative sign flips the arrow in the opposite direction. And it's going to be really important to remember that. Okay, so there it is. And there's a lot of videos on this on YouTube. I posted those in your Canvas. So if you didn't quite figure this, go watch those videos and you'll see. So a scalar times it by a vector does what? All it does, it just changes the length of the arrow. And if S happens to be negative, it flips the arrow in the opposite direction. Okay, by the way, V divided by S, it's the same thing. Because you could say, let's go back. A, what's A divided by 2? Well, this is just 0.5A. So it's just going to tell you, take A and make it half as long. So dividing by a scalar doesn't mean is no added complexity at all. Okay. So I could have written 0.5A as A divided by 2, and then said, well, what this thing does is it takes the length and halves it. Okay. So these two are not bad. It's this one. This is the one that everybody hates, vector summation. Okay, so what we're going to do is erase, and at this point, pay close attention. This. I'm going to let this dry a little bit. I'm going to look for my black marker. It looks the best on the thing. Give me 1 second. Okay, here we go. Vector summation. And by that we mean, we'll call this B1 and B2, two vectors. Oh, I should. How do we do this? We've already done it once. We actually added these two displacement vectors and got a net displacement. We already did this, but we need something that's a little bit more general. Okay, now there are 3 techniques for doing this. We're going to learn all 3. 1, the head to tail. 2, the parallelogram. And 3, the component method. These 2 are easy. This one is real easy. This one's easy, although really not much harder than this one. This one is no fun. The head to tail and the parallelogram are qualitative. They only give you a kind of a general idea what the answer is supposed to look like. If you want the actual real answer with numerical values that are precise, then you have to go to this one, the component method, which is quantitative. We're going to learn these 2 first, then we're going to do the component method. Okay. All right. So we're going to first do the head to tail, and we've already done it. Okay, let me show you. Remind you what we did last time. Let's take out this part. We did the head to tail method when we were talking about displacements. We had a person that was walking along, stopped, and then did another walk along, and we asked, what is the net displacement? What's the total displacement? So we had D1 here, this which is this vector, has a length of this amount, and a direction to the right, and this person went a little bit further, and the total vector when you take D1, I like that, plus D2, was a vector that started from the very start to the end. And this worked even if D2 didn't go straight in the same direction. We looked at it last time. We had D1 like this. And then the person went down ID2. And the same rule was the same here. The vector, the net vector, when you add these two together, went from here, from the start to the tip, the finish. This is B. Make sure you understand that when you add these two vectors, the resultant vector, as they call it, the resultant vector is the result of adding these two. The resultant vector starts from where you started and it reaches to where you ended. It does not go this direction, it goes in that direction. And this is really important because I catch a lot of students making this mistake. They want to draw this blue one to go here to complete the circle. Don't work like that. So what is the rule? Well, you'll notice the tail of this one is attached to the head of this one. Head to tail. So we've already been doing it. So let's draw a couple more vectors, and this time I'll show you what I mean in more general terms. So here we have vector A, just a label. Vector B. And I want to add these two vectors. Okay. The head to tail method says attach the tail of this one to the head of that one. But remember, as long as I maintain the direction of B and its length, I can move it anywhere I want because its length and its direction define the vector. If I don't change either one of them, I'm keeping the same vector. So what I'm going to do is move my vector up to here. And now, to find what A and B are equal to, I draw from the beginning to the end. And I usually will call this vector C, such that vector C is A plus B. Now, I'm going to do the same problem, but I'm going to move the vectors differently. So I'm going to draw the same vectors here. Vector A, yeah, pretty close. And I have vector B kind of like this. But instead of attaching the tail of this one to the head of this one, I'm going to take the tail of this one, attach to the head of this one. So I'm going to move A. So I'm going to move A over here. So vector A. And now my resultant, when I add these two vectors, begins from the very beginning to the end. And I didn't draw it very well. In fact, I did a terrible job. You see, vector B, this vector was supposed to come out exactly the same as this one, but I didn't draw them quite right. So they don't look quite the same. However, if I did this carefully, this vector C and this vector C would be identical. They'd have the same direction and the same length, and which tells you that it doesn't matter which order that you add these vectors head to tail, you get the same answer regardless. So let's do another one. And this time we'll add up like 4 vectors. So here's a vector. Here's another one. I'll just do 3. Here's another one. So this is A, B, and C. How do we add these vectors? Well, we add them up head to tail. So we're going to hook them up in a daisy chain. And so this is going to look like A, I could add B next, but I can do C. Doesn't make any difference. I'll take C, move it down like this. Does that look like C? Oh, a little too hard. And then B. Excuse me. And when I add A, B, and C, oh, I forgot to mark this one. I get this vector from start to finish. We'll call this D. D is A plus B plus C. So you can see if you have 8 vectors, they're just easy to add. You just simply hook them up head to tail and then just draw a vector from the beginning of the path to the very end. That's your resultant vector. Now, what about this vector subtraction? Okay, so what I'm going to do is I'm going to do the same problem. But suppose that I was asked to take D equal A minus B plus C. Oh, shoot, how do we do that? There's a little trick. We would simply say, well, this is just A plus negative B plus C. Instead of subtracting B, I add negative B. I can do that. Subtracting $6 from your wallet is the same as adding negative $6. Same thing. Okay, and now you may think, oh wait, now I know how to do this, because what does the negative sign do? You can't forget this. The negative sign flips the vector. So what does negative B look like? Negative B is B, but flipped upside down. This is B. I'll just draw it over here. Oops. This is negative B. Same as B, but flipped upside down. And now this is negative B. I can just take this vector plus this one. And I have my answer. I'll do it right now. So I have A. I'll add the C next. Ooh. And then I'll add negative B. And my resultant is a vector that points from the start to the finish. That's how you do it. And so vector subtraction is no harder than vector addition. All you got to do is just flip the direction of B and add the negative. Very simple. Now notice though, the head to tail method it's not really good at telling you exactly how long B is. It gives you a general idea. So if you draw these vectors really, really carefully, you might be able to guess the length of D and its direction to some level of precision, but it doesn't mathematically crunch it out for you. That's a weakness in the head to tail method. Okay, that's the head to tail method. And now we're going to talk about the parallelogram method. Okay, so we're going to go back to 2 vectors. Let me do some squirt and start that up. I have again posted a lot of videos on this stuff on Canvas. So if you're really struggling, you could go to Canvas and watch those videos. That might help you. And I also have office hours tomorrow at 1 o'clock, Tuesdays and Thursdays at 1 o'clock every week. Okay, now I'm going to introduce another physics problem that kind of is a nice segue into the parallelogram method. For the head to tail method, I used displacement. a person walking along one trip and then walking in a different direction. And what was the question? It's what is the total displacement? And for the parallelogram method, I'm going to use velocity. Okay, so I'm going to now define velocity. Velocity and speed are not the same thing. Velocity is a speed plus direction. The speed is how fast, and the direction is the direction of travel. This is not necessarily the same direction used in the displacement. I'll show you why. We can represent this with a vector. We'll call this vector v. It's the velocity vector. The length of this vector represents how fast. So if an object is traveling really fast, we would want to use a longer arrow than if the object is traveling really slow, okay? And the direction that the arrow points is the direction in which the object is traveling. Now, you may think, well, isn't that direction of the displacement? No. Let me show you why. And we're going to talk about this in more detail later. But suppose I take my object and I throw it. And let's say it's like a cannonball, and you shoot a cannonball out of a cannon. What does it do? Well, here is the ground. Here's my cannon. It's like, it looks like more like a mortar, but okay. Here's your cannonball. And the ball does what? It goes like this. All right, now, let's examine when the cannonball is right here. The displacement vector describes the location of this cannonball, how far away it is from an origin where it started, in this case, although we could make it somewhere else, but we're usually you want to describe the displacement from where it started. The displacement is a vector that points from what? Where it started to where it is. And therefore, this is your displacement vector. The velocity vector is how fast it's traveling and in which direction it's traveling. And therefore, this is the velocity vector. Why? Because right here, the object is traveling in this direction. Let me see, clean that up just a little bit. The object is traveling kind of in this direction, and therefore the velocity vector points in the direction of travel. But look at the direction. The direction of the displacement is this direction here. It's the direction at which you have to point towards the object where it's located. The direction of this vector is this angle here. Completely different directions, okay? And when we do projectile motion later, we're going to have to remember that. It fouls students up all the time. I'll ask students, well, in what direction is the object traveling? I'm like, I don't know. Find the velocity vector. The direction the velocity vector points is the direction that the object is traveling. Maybe you should remember that. Chad, write that down. Put it on in your notes. It's good to remember. The direction of the velocity vector, the direction the velocity vector points, is the direction that the object is traveling. It is not the direction where the object is located. Different things. So we have a little bit of an idea about this. What about the speed? Well, we can measure this speed is again how fast, and we have units for how fast. Remember, you have CGS, the MKS, which is also called the SI. The CGS unit is centimeters per second. And the MKS is in meters per second. And you should have a good handle on about how fast these things meet. What is 1 centimeter per second? Let's see here. A centimeter is about the width of your pinky, the fingernail on your pinky, and it's taking it 1 second to traverse. So every second it travels across one pinky. So this thing is moving kind of like that. That's about a centimeter per second. A meter per second means that it's traversing this length in a second. Okay, so if I put this up here, 1001, 1001, 1001. So this is about a meter per second. There's about a 1 meter per second is roughly 2 miles per hour. And if you know about walking, if you ever do any exercise, like you can tell I do all the time, of course, you're thinking, man, that dude, he probably gets up in the morning, like 5 o'clock in the morning and jogs 10 miles, right? That's what you're thinking, right? Then you'd be right. I mean, I get up at 5 o'clock in the morning and I get up and I walk. Okay, so what is that? Well, about like this. Okay, it's hot. Let me take a look at that. It's about like this. This is about 1 meter per second. So that gives you a good idea about how fast is fast here. Okay, now, what about adding velocities? When would we ever do that? Well, here's a good problem where we do this. Let's see here. Go ahead, get the squirt. Right. Okay, so here we go. We're at a boat. And we have a river. And this river, water is flowing. Well, let's make it not flowing at all initially. This is a river where the water is pretty much perfectly still. And we're going to take our boat and we're going to drive it across at 10 meters per second. So we're going to go like this. I'll tell you what, let's go up. Okay, so here we go. We're going up this one here. This is at 10 meters per second. Now, suppose all of a sudden the water's turned on and the water is going to travel along here at 5 meters per second. What do you think is going to happen to our speed? Well, when we have 10 and all of a sudden the water is pushing it at an extra speed, we would think that this is going to give us a net speed of 15 meters per second. Now, again, here's where you have to talk about in terms of reference frames. So if a person is standing here on the side and he's watching, and we'll have no water motion, and you're in the boat, green boat, this person will see you traveling by at 10 meters per second. Now, what if we turn the water on? At 5 meters per second. Then this boat is going to get a tailwind, when I say a tail current, it's going to make it go faster. This person will see this boat traveling down the stream at 15 meters per second. Does that make sense? Hopefully that makes sense. Okay. What if we try to go across like this? Well, okay, let's do that. And initially we have no water, and we're just going to take our boat and we're going to go across at a speed of 10 meters per second. This is our velocity vector V1. The length of the arrow represents the speed, 10, and the direction is the direction in which we're traveling. And I don't want to think that the arrow has to emanate from here. Okay. Now, what if we turn on our water? Now, water gets turned on here, and it's going at 5 meters per second. What happens to the boat? Well, the boat doesn't go straight across, does it? It goes along in this direction. How do we find it? Well, this is a vector here that has a length of 5. So this is V, let me call this one V of the boat, and this is the V of the water. What is the net velocity that you get when you have the water making your boat go downstream? We take this one, add it to here. So this is V water. Remember, I can move my vector as long as I maintain its length, which is how fast, and direction. And the net is this velocity. What does this represent? The direction that the red arrow points is the direction of travel. Don't forget that. This is the direction that the boat will travel across the river. The length of it is how fast it will be traveling in relation to this person watching. So this is 10. This is 5. This looks like it might be 11 or 12 meters per second. How do we find it? Well, this is 90 degrees. We said it was. And therefore, the net speed here is the square root, remember, Pythagorean theorem, of 10 squared plus 5 squared, which is the square root of 125. And that's just a little bit, pretty close to 11 meters per second. Very close to 11. So the boat is going to travel in this direction at 11 meters per second. Now notice that we use the head to tail method here. I could have done it slightly differently. I'm going to recreate this problem. I have my velocity of the boat. Well, what I could have done was taken this 5 and placed it here. Velocity of the water. The net velocity, when I add these two, is found by forming a parallelogram. Hence the term parallelogram. The net velocity is found by going from the corner where the tails, where they meet up, to the far corners of the parallelogram. So I should write down the equation here. V net is equal to VW plus VB. When I add these two vectors, I form a parallelogram and I draw a vector that starts from the origin of all of them to the far corners of the parallelogram. And I get the same answer as if I did the head to tail method. Why? I'll let you think about that. Why do I get the same answer as we did before? Think about it. If you'll notice, this vector here is the same as this one, because this is a parallelogram. Therefore, this is just the head to tail method. The head to tail and the parallelogram are essentially the same thing. And you may be wondering, well, why do I need the parallelogram method if I already have the head to tail method? When we do the component method, which is next time, we'll see why we do that. Okay? There is a reason. However, we don't have to worry about it for the time being. So let's do a practice problem now with the parallelogram method, and then we'll call it a day. If you're not sure what I'm doing here, this will help. I think I was a little out of sorts there, so I know I have to kind of explain this a little bit better than I was doing. All right. We have vector A and vector B. How do we add these vectors using the parallelogram method? Instead of taking the head the tail of this one and attaching it to the head of this one, we instead attach the tails together. Hey, well, I'm going to make this vector a little bit longer so that this thing, I can draw it. So I'm going to take B and I'm going to move it down to here. So now I'm going to attach the tails together. You could call the parallelogram method the tail-to-tail method as well. And then I'm going to form a parallelogram out of these two. By the way, I have moved B, so it's no longer here. It's not here. And now I'm going to form a parallelogram. Think of it as a crushed box. Ooh, out of control. Well, that's pretty good. This side has to be parallel to this side and the same length. This side has to be parallel to this side and the same length. It's like a crushed box. When I add A and B, I get this vector. It goes from the tails to the far reaches of the parallelogram. So if this is vector C, the resultant vector, then C is A plus B. Now, could I have done this with the head to tail method? Yes, I could have taken B and instead of moving it to where the tails meet, I could have moved it to here, but then I would have just got this vector. And I would have got the same answer. So that there is good evidence that the head to tail and the parallelogram method are in fact really the same thing. Now, the advantage of the head to tail is that I could hook up a whole bunch of vectors, head to tail, a lot easier than I can do with the parallelogram method. With the parallelogram method, I would have to take these two vectors, add them to get C, and then take the next vector and add it to C and get that answer. So if you're dealing with multiple vectors, more than two, then the head to tail method is a lot easier. But technically, they're the same thing. All right. All right. I think that should do it for the day. It's a lot to cover. Again, if you're not sure about the, let's say if you're not quite sure, you're not having quite followed this very well, then do yourself a big favor and go on to the YouTube videos that I posted. They're pretty good. They'll walk you right through all of this. Okay. Until next time, I'll see you later.